Have you ever stopped to think about the invisible forces, the really powerful ones holding our world together?
Yeah, and probably not the one you first think of.
Exactly. We're not talking about gravity here. That's kind of the weakling in the cosmic family photo.
Yeah, no, we're diving into electricity and magnetism. These are the behemoths.
Force is so gigantic, they have to be balanced with just mind-boggling precision. Otherwise, matter itself wouldn't hold together.
That's the perfect starting point. We're doing a deep dive today, straight into the foundational ideas from the first chapter of the Feynman Lectures on Physics, Vol.2.
Right, the classic.
And our goal really is to distill the core physical concepts, the key relationships conceptually, without getting lost in the math that you need to grasp electromagnetism as, well, a single unified field.
Okay, let's jump in. Section 101, electrical forces. We know it follows an inverse square law like gravity, but the strength, the analogy Feynman uses is just stunning.
It really is. It hammers home the sheer scale difference. Okay, imagine this. You and I are standing, say, arm's length apart. Now suppose, just suppose, each of us had 1% more electrons than protons. Just a tiny imbalance.
Okay, 1%. Doesn't sound like much.
The repulsive electrical force between us from just that tiny imbalance would be strong enough to lift a weight equal to the entire Earth.
Wait, hang on. Lift the Earth?
The entire planet, yeah.
That's almost unbelievable. It means the positive and negative charges in everything in us, in this table, are balanced out to an accuracy way, way better than 1 part in 100.
Exactly. It's an astonishingly precise cancellation. If nature were just a tiny bit sloppier with charge balance, everything would just, well, explode from repulsion.
So the fact that matter is stable is down to this near-perfect charge neutrality. We only really notice electricity, like static or lightning, when that balance gets slightly upset locally.
That's the crucial idea. It's usually perfectly balanced.
Okay, but that brings up a huge question, one the chapter tackles right away. What about the nucleus of an atom? It's packed with positive protons. They should repel each other with that same enormous force. Why doesn't the nucleus just fly apart instantly?
Ah, good question. And that's where nature throws in another layer. There are other forces at play, much stronger than electricity, but only effective over incredibly short distances.
The nuclear forces.
That's right. Specifically, the strong nuclear force. It's powerful enough to overwhelm that huge electrical repulsion within the tiny confines of the nucleus, holding the protons together.
So electrical forces dominate at everyday distances, but nuclear forces rule the subatomic core. Okay, that makes sense for why things stick together.
It sets the stage for stability, yeah.
All right, so let's move from static charges to moving ones. Things get more complicated then, right? We need a law for the force, math be a charge brawler, that's moving with some velocity, math BFE.
We do. And this is the fundamental electromagnetic force law. Conceptually, it says the total force on that moving charge comes from two different things added together.
Okay, 2 parts.
First, there's the electric force. That depends on the electric field, which we call math BFE. Pretty straightforward. Second, there's the magnetic force. And this depends on the magnetic field, math BFB. But crucially, this magnetic part also depends on the charge's velocity, and math BFE.
So no movement, no magnetic force on the charge.
Exactly. The magnetic force only affects moving charges. And the direction of that force is tricky. It depends on both the direction of math BFE and the direction of math BFB.
Okay, math BFE plus math BFE plus math BFB. We won't get lost in the cross product math, but conceptually. Electric part plus a velocity-dependent magnetic part.
That's the essence of it. And how do we handle situations with lots of charges making these fields?
Superposition always comes to the rescue.
It does. It's a huge simplification. The principle of superposition just means that the total math BFE field, or the total math BFE field, at any point in space is just the vector sum. You just add up the arrows, basically, from all the individual charges contributing.
So we're dealing with math BFE OE and math BFB as vector fields. Now, we might know a scalar field, like temperature, just a number at each point. How is a vector field different?
Well, a vector field gives you more. At every single point in space, 6, x, y, z, z, and it can change with time, too. It gives you not just a magnitude, a strength, but also a direction.
Like wind velocity on a weather map. You see the speed and the direction the wind is blowing everywhere.
Perfect analogy. It's directional information mapped across space.
And Feynman shows ways to visualize these, right?
Yeah.
Because we can't actually see the fields.
Exactly. 2 main ways. You can draw little arrows at various points. The arrow's length shows the field's magnitude or strength, and the way it points shows the direction.
Okay, arrows. What's the other way?
Field lines. These are continuous lines drawn so that the line is tangent to the field direction at every point along it.
Ah, so the line itself shows the direction. What about a strength?
The density of the lines. Where the lines are crowded together, the field is strong. Where they spread out, the field is weaker. It's like mapping flow.
Got it. Arrows or lines density. Okay, this language of field sets us up for the next crucial step, moving from just describing fields to understanding the laws they obey. And for that, Feynman introduces two key mathematical concepts, flux and circulation.
Right. These are the tools we need to talk about the fundamental properties of vector fields, which then lead directly to Maxwell's equations. Let's take flux first.
Okay.
Feynman uses the analogy of fluid flow, which is really helpful. Imagine you have some kind of closed surface, like an imaginary sphere or box in space.
A boundary.
A boundary, yes. The flux of a vector field, say math BFE, through that closed surface is basically a measure of the net amount of field lines poking out of the surface.
Net amount out. So if more lines go out than in, the flux is positive.
Exactly. It's the average component of the field perpendicular to the surface times the surface area. Think of it as measuring whether there's a source or a sink of the field inside your closed surface.
Like a faucet inside the box, spewing field lines out, positive flux, or a drain sucking them in, negative flux.
That's a great way to picture it. Flux tells you about sources and sinks inside a volume.
Okay, that's flux. What about circulation?
Circulation is different. Instead of a closed surface, we think about a closed loop or curve in space, like an imaginary rubber band.
Okay, a loop.
Circulation measures how much the vector field tends to swirl or circulate around that closed loop.
Like water swirling in a drain.
Precisely. It's the average component of the field that's tangent to the loop, multiplied by the length of the loop. It tells you how much the field goes along the curve.
So flux is about flow through a surface, sources. Circulation is about flow around a loop, swirls.
You've got it. And these two concepts, flux and circulation, are exactly what we need to state the four fundamental laws of electromagnetism in a really insightful way.
Maxwell's equations, but framed using flux and circulation. This is where it all comes together.
This is the core. Let's go through them. Law number one concerns the flux of the electric field, math BFE. It's Gauss's law for E.
Okay.
It states that the total electric flux out of any closed surface is directly proportional to the total net electric charge sitting inside that surface.
So electric charges are the sources and sinks of the electric field. More charge inside, more net flux out. No net charge inside, zero net flux.
Perfectly stated. That law nails down where math BFE fields come from.
All right, law number two, about the magnetic field, math BFB.
This one's about the flux of math BFB. It's Gauss's law for B, and it's remarkably simple. The total magnetic flux through any closed surface is always zero, period.
Always zero. What does that mean physically?
It's profound. It means there are no magnetic charges, no isolated north or south poles, what we call magnetic monopoles. Magnetic field lines don't start or end anywhere. They always have to form closed loops.
Okay. So if a field line goes into a closed surface, it must come back out somewhere else on that surface. Net flow is always zero. No magnetic sources or sinks.
Exactly. No monopoles found, ever. That's law 2.
Okay, laws 1 and 2 deal with flux sources. What about circulation? Swirls, that's laws 3 and 4.
Right. Law 3 is about the circulation of the electric field. Math BFEI. This is Faraday's law of induction.
Faraday. Changing magnetic fields, right?
That's the one. It says the circulation of math BFE around any closed loop is proportional to the rate of change of the magnetic flux passing through the surface bordered by that loop.
Whoa, okay. So if the magnetic field through my loop is changing, getting stronger or weaker, or changing direction that creates a swirling electric field around the loop.
Precisely. A changing magnetic field induces an electric field. This is the basis for electric generators and transformers. It connects magnetism back to electricity.
That's huge. Okay, one law left. Law 4 must connect electricity back to magnetism using circulation.
Yes, it's about the circulation of the magnetic field, math BFBFE. This is the Ampère-Maxwell law, and that Maxwell part is key.
What did Ampère have, and what did Maxwell add?
Ampère knew that electric currents create magnetic fields that circulate around them. So the circulation of math BFBO around a loop is related to the electric current poking through that loop.
Okay, currents make B fields. Seems reasonable.
But Maxwell realized something was missing for consistency, especially when dealing with capacitors or empty space. He added a second term. The circulation of math BFB is related to the electric current, plus another term proportional to the rate of change of the electric flux through the loop's surface.
So just like a changing B field creates an E field, Faraday, Maxwell realized a changing E field also creates a B field.
That was the crucial insight. That second term, the changing electric flux, also generates a circulating magnetic field, just like a real current does. This completed the symmetry and unified the laws.
And that addition had massive consequences, right? Like predicting electromagnetic waves.
Yeah.
Light itself.
It's the key that unlocks light, yes. These four laws, unified by Maxwell, describe all of classical electricity and magnetism.
Amazing. Okay, let's ground this a bit. The chapter uses examples like wires carrying current. How do those illustrate these field interactions?
Well, think about two parallel wires. If you run current through both in the same direction, the wires actually pull towards each other, they attract.
They attract. Why?
Because the current in wire 1 creates a magnetic field that circulates around it. Wire 2, carrying moving charges, the current, is sitting in that math BFB field. According to the force law, math BFB1 part, there's a force on wire 2's charges directed towards wire 1.
And vice versa, wire 2's field pulls on wire 1.
Okay, right. And if the currents are in opposite directions, the force pushes them apart, they repel. It beautifully shows currents creating fields and fields exerting forces on other currents.
It makes the fields feel more real. Which leads directly to that philosophical question Feynman raises. What are the fields? Are they just mathematical bookkeeping, or are they physically real things existing in space?
Yeah, it's a fundamental question. Historically, there were two main ideas. One was action at a distance, like gravity was often thought of. The force from charge A just instantly appears at charge B, leaping across the empty space. No intermediate thing needed.
Okay, direct connection. What was the other idea?
The field concept. The idea is that charge A creates a condition, a physical entity, in the space all around it, the field. This field exists everywhere. Then charge B, sitting in that field, feels a force from the field at its location. The field mediates the interaction.
So the field is the intermediary. Which view wins out?
The field concept, definitely, especially when things are moving fast. If you wiggle charge A, the effect on charge B isn't instantaneous. The news of the wiggle travels outward through the field at a finite speed.
The speed of light.
The speed of light. The Seiler. The action at a distance view just couldn't handle this propagation delay correctly without becoming incredibly complicated. The field carries energy and momentum. It seems to be physically real.
And you mentioned light. This ties into relativity too, doesn't it? That constant T2 pops up in the relativistic version of the force law.
It does, and this is maybe one of the most mind-bending insights. Magnetism, in a deep sense, is actually a relativistic consequence of electricity.
How so?
When you look at the force between moving charges from different reference frames, say you're moving alongside the charges, versus standing still, lengths contract and time dilates according to special relativity. To make the laws of electromagnetism give consistent results for all observers, regardless of their motion, you need the magnetic field terms. The magnetic force involving 1c2 is precisely what's required to account for the relativistic effects on perceived charge densities and forces.
So magnetism isn't fundamentally separate from electricity. It's how the electric force manifests itself when you account for the principles of relativity and the finite speed of light.
Wow. Yeah, it's deeply interconnected. In fact, the need to make Maxwell's equations work in all reference frames was a major driver for Einstein developing special relativity in the first place. Electromagnetism was already relativistically correct. It was classical mechanics that needed fixing.
Incredible. Okay, so let's try to wrap this up for you, the listener. What are the absolute key takeaways from this foundational chapter?
I'd say two main things. First, the fundamental force on a charge involves both an electric field, math BFE clue, and a magnetic field, math BFE, with the magnetic part depending on velocity, plus math BFB, plus math BFV times math BFB. Second, the behavior of these math BFE clue and math BFB fields themselves is governed by the four Maxwell's equations, which can be understood really intuitively using the concepts of flux, how fields emerge from sources or loop, and circulation, how fields swirl around loops or changing fields of the other type.
And the historical impact of figuring this out. It's hard to overstate, isn't it?
Absolutely. Feynman notes that harnessing these subtle electromagnetic effects, governed by these laws, led to everything from tiny instruments to global communications, telegraph, radio. He argues Maxwell's synthesis might just be the most significant scientific event of the 19th century, profoundly changing human civilization.
Which leaves us with maybe a final thought for you to chew on. These laws came from studying seemingly simple things, like static cling and magnets. Yet they revealed the nature of light itself and underpin, well, basically all of modern technology. How amazing is it that understanding the abstract geometry of invisible fields and the dance of electrons has given us the power to reshape our entire world?
Something to think about. Thank you for joining us for this deep dive into Feynman's opening chapter.
We hope this gives you a solid conceptual footing for exploring the fascinating world of electromagnetism.